Great. Thanks to the organizers for inviting me and putting on this nice meeting. So I'm on the qubit side of it from qubit. And I'll tell you about some questions that are motivated by quantum computing, but I think also will be relevant to a lot of the things of like random unitary circuits that appear in this intersection of fields. A lot of the motivation can be related to, I mean, it started before this work, but I think came up in this newsworthy story by the Google team, where they announced they had performed a task on a quantum computer, a programmable quantum computer that they claimed could not be done by any reasonable classical computer. And IBM, to give you a sense of how impressive this was, IBM pushed back and said that actually Google had overstated the difficulty of doing it classically. You could do it on a classical supercomputer with only 2 to the 70 operations. So I think that's sort of the state of quantum computing today. It's not a useful task, but neither are the benchmarks that they run on graphics cards. It sort of demonstrates that quantum computers can, for the first time, do something that my laptop cannot simulate. And what is the task? It is, so here's physically what the chip looks like. Here's a schematic. The little X's are qubits, and the blue things are couplers. If you zoom in, it looks like this. And what they do is they do this quantum circuit, which means a series of unitary quantum gates. These little boxes are single qubit unitaries. These couplings are 2 qubit unitaries. They measure at the end. And that's all they do. They just measure. They run the circuit for a while. They measure everything. They get a probability distribution, and they claim that this is hard to simulate classically. So this is a theory conference, so let me get rid of the pictures of circuits and show you more of a schematic version. So I kind of like time to go from right to left, because it looks more like bracket notation. So you start with a bunch of zeros. This is what a quantum circuit looks like. You do a series of unitary gates, and you measure. The probability is this quantity here. A few relevant quantities are the number of qubits n, the depth of the circuit t, which is like the complexity that you just heard about, and other parameters that when you're evaluating quantum computers, you might care about are things like the connectivity, the total number of gates, not just the circuit depth, and the fidelity. But those, I guess, are relevant when you're evaluating quantum computers, and also when you're talking about the complexity of the sampling problem. So I'm interested in how hard is this really to do on a classical computer. Those are all determined by these other quantities as well, which I'm not going to explore in this work, but I want to mention that those are, if you look broadly at how hard it is for classical computers to sample from the output of quantum circuits, those are also relevant. So here's another schematic of what Google did. You have a 2D array of qubits. You do a series of quantum gates, and then you measure. This output distribution P of z, there are conjectures that it's hard to sample from a classical computer. There's a conjecture which I guess I'm calling it the Google conjecture, even though it really came out of the quantum computing community more broadly. And there's a general conjecture that if the depth of the circuit scales like root n, the classical simulation time should be roughly exponential in n. You shouldn't be able to do much better than just a naive full simulation. And so what I'll tell you about today are 2 results, my sort of 2 different takes on this. The first one is the regime of deep random circuits. So when if you have a random circuit in, let's say, d spatial dimensions, then we show that the time it takes for it to be what's called a k-design scales like the diameter of the circuit. So root n if it's on a 2D grid. And this supports Google's conjecture. Their conjecture is that it's computationally hard. Some aspects of that are going to rely on questions from computational complexity theory that are likely to remain open, kind of along the lines of p not equal to np, but actually substantially more challenging than proving p is not equal to np. So those you could leave as plausible conjectures from complexity theory, but part of it is a relatively tractable problem of, do these circuits form k-design? Something I'll define a little bit later. So the first result I want to present is that we prove that in the regime where the amount of time is long enough for a signal to pass from one end of the system to the other one. so this is sort of evidence in favor of the Google conjecture that their thing is hard to simulate. In the other direction, I also want to consider shallow random 2D circuits. So we know that if you run, so what happens if you run it for a very short amount of time? We know that in the worst case, this is hard for a classical computer to simulate. And in general, people have kind of assumed that random circuits and worst case circuits are equally hard to simulate. And I will show something short of a full proof, but I hope you'll believe pretty convincing evidence that random circuits are way, way easier to simulate than worst case circuits in this regime. And this, I think, is an example of, there are probably many other examples where random circuits are easier to simulate than worst case. So that is the overview. Two different takes on how hard is it for a classical computer to simulate what a quantum computer does. And for the first part, I'm going to talk about how random circuits, once they're deep enough, basically behave like the Haar measure. So if you have not seen the Haar measure before, basically what I mean by that is the uniform measure over some group. In this case, it'll be the group of unitary transformations on 2 to the n dimensions. And part of why it's so great to reason about is it obeys nice properties like measure concentration. If I have any function with bounded gradient, and I draw u randomly from the Haar measure, it's super likely to be very close to its expectation. However, I cannot do the Haar measure in any either a quantum computer or any natural system. It's not a reasonable model of either natural or artificial dynamics because it takes exponential time. And this is not a particularly quantum observation. Classical random functions also require exponential time, just because there's so many different, there's so many of them. There are a lot of random matrices, random unitary matrices. There are not that many short quantum circuits. So just by a counting argument, we cannot expect to get something close to Haar measure in a reasonable amount of time. But for many applications, it's often overkill. So let's suppose I draw a random qubit from the Haar measure, and I take the density matrix from that ensemble. That's just the maximally mixed state. And I get that same density matrix by averaging over 2 discrete states, spin up and spin down. Of course, when I go to the second moment, this spin up, spin down ensemble no longer works. If I take a random state here, I get the average over the triplet, a 3-dimensional state. And here, of course, the thing is rank 2. And so, and the second moment already turns out to encode a lot of useful information. So if I take psi to be a random state, now let's say it's from a bipartite system. It's got an A part and a B part. And I look at the expectation of trace psi sub A squared. Psi sub A is the reduced density matrix on the A part. And I look at the expectation of trace of this thing squared. It gives you some number. You can exactly calculate it for the Haar measure. And it turns out knowing this is already enough to show that these states have near maximal entanglement. It gives you something pretty close to the Page formula. Not exactly. That's for von Neumann entropy. This is for something related to Rényi entropy. But if you just care about showing it's very close to maximally entangled, this will already do the job. And you'll notice this relies only on the second moment of these states. So the first moment gives you the density matrix. The second moment gives you things like the property of near maximal entanglement. And so if I can control things like this expression right here, the expectation of 2 copies of ket psi and 2 copies of bra psi, I can already learn quite a bit. So maybe I don't need the Haar measure. I just need the low order moments. And so this gives rise to this motivates the definition of the K design. A unitary K design is a distribution that matches the first K moments of the Haar measure. So more formally, if I have a monomial, when I say K, I mean really K copies of U and K copies of U star. I want a distribution mu such that if I take the expectation of that monomial, I get the same answer under mu that I would for the Haar measure. And I can also express this in terms of a single matrix. So I can take G sub mu to the expectation of U tensor K, tensor U star tensor K. The matrix elements of this thing encode all of these monomials. And so if G mu is equal to if G sub mu is equal to G sub Haar, then this thing is a K design. And I often am happy even with approximate K designs where these matrices are approximately equal. Any questions about this definition? So what are some applications of this? Well, k equals 2 already gives us quite a lot. And I've worked on variants of this problem for a while. And it's often hard to justify going beyond k equals 2, because you get so much from that. You get decoupling, which I didn't explain it, but this is relevant to the Hayden-Preskill black hole as mirrors argument that uses decoupling. The out-of-time order correlator, if you look at it, you see there are 2 copies of U and 2 copies of U star. So that's also relevant to the second moment. Entanglement, I mentioned already. For this quantum supremacy application, the connection there is that Google's conjecture relies on the output of the quantum circuit satisfying something called anti-concentration, which basically means if you look at those output probabilities, they should be pretty close to uniform. Their entropy should be close to maximal. In particular, this is a statement about their Renyi entropy being close to maximal. There are a number of equivalent statements that will all basically work as long as they have decent fidelity with the uniform distribution. All those follow from k equals 2. For higher k, you get some applications as well. Some people in the qubit community have used it to get circuit complexity lower bounds. It implies some concentration of measure bounds that are certainly weaker than you get for the Haar measure, but increase in strength as you increase k. So there are a number of applications of these, and we would like to know when do we get these from plausible models, either that we can implement artificially on a quantum computer, by programming in all the gates, or that might be a reasonable proxy for random dynamics. Now, a real system might have a time-independent Hamiltonian, and I'm going to consider random circuits where we draw fresh randomness in each round. However, you might argue that for a chaotic Hamiltonian, this is not a terrible approximation. Anyway, that's certainly an interesting question to improve on in the future. So the first result, which is, I guess, by now a little bit old, is that for a 1D random circuit, if you have n qubits in depth t, and the circuit model I'll consider is that on nearest neighbor gates, I do just random 2 qubit unitaries. I guess the result also holds if you replace qubits with higher dimensional particles, but just for simplicity, I'll present it with qubits. Then with Fernando Brandão and Michał Horodecki, we showed that you get a k design after a time that scales linearly with the number of qubits and polynomially with the order k of the k design that you want. This polynomial in k is almost certainly not optimal. And I think Nick Hunter-Jones has an argument why it should actually be linear in k, which seems more plausible, I think, as the correct answer. We just have an upper bound on the number of gates that you need. In 2 or more dimensions, Saeed, my former student Saeed Maraban, who's here right now, and I showed that basically the same result holds. A few more asterisks, which I don't want to get into right now, but nearly the same result holds if you, in higher dimensions. So if you're in d spatial dimensions, the depth that you need goes like n to the 1 over d. So square root of n in 2 dimensions, cube root of n in 3 dimensions, and so on. And I think I'm going to probably skip the proofs. It required some pretty substantially different proof techniques than our previous result. Yeah, but I think I won't get into why the proof is different. But anyway, it uses the previous result as a subroutine, but then had to do some new things. And after doing this, you might think, well, look, of course, the time to mix up a system is just going to be how long it takes from a signal to get from one end to the other end. Like that's the time it takes for any one part to interact with any other part. So, why are you writing these long papers proving this thing that we already kind of believe? And I tried for a little while to prove that it should be true for just a general geometry. Like if you put qubits on any graph, the time to get a k design should just depend on how long it takes for a signal to get from one end to the other. And I want to present to you an example where this is not quite true. So this is a paper by Peter Shor, where he considers the photon sphere of a black hole, and he makes it into a graph in a kind of funny way. He says, take a region that has one bit of Hawking radiation in it and call that a cell. And if you do that, you get kind of big cells on the outside, and you get the cells getting to be smaller and smaller as you move in. The number of qubits, the number of cells, goes like m squared. If you take a circle at height h above the horizon, then you get root m over h cells. And the distance to escape goes like log of m over h. So it's a graph where the diameter of the graph, the time to get from one end to any other end, is log n. They're very quick paths between any 2 points. But you have to go via these outer cells. And maybe a good example of this would be a skyscraper with an elevator. To get from one floor to any other floor, you can do it very quickly, but you can't all exit the building at the same time. And I should mention, this is not meant as a plausible, well, I don't know if Peter meant it. I don't want to claim this is a plausible model of black hole dynamics because, this is empty space, and the Hawking radiation probably doesn't interact with itself very much. Maybe all the interactions happen at the horizon. So I'm going to analyze nearest neighbor gates on this graph. That's not necessarily meant as a model of black hole dynamics, merely an example of what happens in this funny kind of geometry. So this geometry resembles a little bit an even simpler one, which is just a binary tree, right? Also has log n diameter, but to get from, there is a bottleneck. All of those log n paths require this top vertex. And now we can ask some questions related to two designs. One of them is the OTOC time. If I have an operator A at one end and B at the other end, how long if I Heisenberg evolve operator A until it has a non-negligible commutator with B? Or I could ask how long till the left subtree gets pretty entangled with the right subtree. And what we showed is that the OTOC time kind of more or less scales like diameter for a completely general graph, as long as the graph degree is not too big. So the degree means if you have a qubit on one vertex, how many other qubits does it connect to? That number cannot be too large. If that's true, then the OTOC time is basically the diameter. So for tree and Euclidean space, that's n to the 1 over d. This photon sphere, for the tree it's log n. For the Euclidean space, it's n to the 1 over d. Photon sphere is also log n. However, the entanglement time can be different. For Euclidean space, it's roughly the same. But the entanglement time, you can just see for the tree, the time for the left subtree and the right subtree to interact, they can only, in each time step, they can only generate one bit of entanglement between the left and the right tree. And there's n vertices. So the amount of time has to scale like n. And similar arguments apply to the photon sphere. The time for the left and right halves to get highly entangled should scale like root n. So the entanglement time and OTOC time both are aspects of two designs, but they can scale very differently and differently than the graph diameter. And so this means that general graphs can have scrambling time that is quite different than their diameter, and also can depend even within a particular value of k, even for two designs, on the actual measure of being a two design that you use. And things are even worse if you have high degree. For high degree, it can really, even the OTOC time doesn't have to look like the diameter. So yes, this is my first result that I want to present. And I think because I want to leave time for the second result, and I know I'm standing between you and lunch, I will skip the proof. Maybe I'll just very briefly say for our old result, you can interpret this. Basically, you want to show that the random circuits on one dimension form a k-design. You can relate that to the spectral graph of a nearest neighbor Hamiltonian on a line. And you want to show that the spectrum of this thing has a gap. And you can do that by appealing to results from the condensed matter literature and playing around with permutations. So I'll skip the details of that. And for my work with Saeed on higher dimensions, we basically need to be very careful with matrices and norms of matrices. So I will leave that to question time if you want to know more about that. And I want to move on to low depth circuits. So if you go back to what I started with, Google claimed that on a root n by root n grid, if you run for time root n, it is, you cannot do better than naive exponential. And it's a question that's of both theoretical and practical interest of how low can you make the depth. Practically, it's interesting because these qubits are noisy and they don't survive for very long. And theoretically, we would like to know the boundary between what is classically simulable and what is classically hard. I think Google wanted to be safely in the regime of what is hard. They were not interested in sitting at that boundary. But as a theorist, I would like to know, when exactly do things become computationally hard? And there was a paper which I think was ahead of its time by Barbara Turhall and David DiVincenzo that showed as soon as your quantum circuit is depth 3, it becomes hard to exactly calculate the output probabilities and even hard to just exactly sample from the output distribution. If you do depth 2, it becomes kind of trivially easy because, even then it's kind of interesting. If you do depth 2, then any quantum circuit will look like it's on a ring. And as I'll show in a minute, constant depth circuits in one dimension are easy. There's sort of a realization of the Turhall-DiVincenzo result using an idea called measurement-based quantum computing due to Rausendorf and Brown. And the idea there is you prepare something called a cluster state. What you do is you just have each of these spins be basically pointing spin right, and they talk to each other with a ZZ coupling. You evolve that for a short amount of time. And so in constant time, you get a big entangled state. And then what they showed is that you can use this as a resource to do any arbitrary quantum computation in the following way. You have this line of L qubits, and you measure them row by row. So you measure the top row, then the second row, and the third row, and so on. You're doing single qubit measurements. As you do this, it will simulate a 1D quantum circuit of L qubits proceeding for time w, so proceeding downward in the direction of your measurements. These measurements have to be adaptive, so you have to look at the results of your measurements and adjust the second round, your subsequent rounds of measurements based on that. But otherwise, it reduces the amount of technology that you need to do this. And this implies, if I want to simulate this constant depth circuit, which could be create the cluster state and do the measurements. I can do all of that in constant depth. Then that's at least as hard as simulating a quantum circuit on L qubits evolving for time w, or evolving in the other directions, w qubits evolving for time L. So the complexity should at least be exponential in the minimum of L or w. And this can be achieved as well. So this argues it's at least that hard, and also there's an algorithm that achieves it. And the algorithm is tensor contraction. So let's go back to this circuit picture. If you look at this circuit, every one of these unitaries you can think of as a 4-leg tensor. It's a matrix with 2 qubits coming in and 2 qubits coming out. It's also just a tensor with 4 indices. And if I contract them in the right way, I might be able to improve on the naive simulation. And let me show you how that works in 1 dimension, where it works pretty well before we move on to the 2 dimensions. So let's suppose I have a 1D circuit. I start with n qubits in the 0 state. I do something for depth t. Think of t as very small here, like 3 or 4. And then I measure everything, and I get answers z1 through zn. And let's say I want to compute the probability of getting a particular outcome. So some fixed z1 through zn. The case when I want to sample from the distribution is pretty similar. Then I have basically a rectangle of size n by t, and it's full of little tensors that I want to contract together. And so I have to pick some ordering of how I contract it, and there are 2 natural orderings. I can sweep across horizontally or vertically. If I do it horizontally, then the intermediate tensors are going to look like this. They're going to have n dangling legs. And to write that down, I'm going to need 2 to the n complex numbers, right? Because each leg is 2-dimensional. And so the runtime of that is going to be exponential in n times t time steps. So actually, pictorially, it's going to look like this. So here's my little rectangle of tensors. Here's my intermediate step. As I sweep across, that's what it does, right? It sweeps across in that direction. And this basically corresponds to the naive simulation where I just write down the whole 2 to the n dimensional state and just evolve that forward in time. But I can go in the other direction too. I could I could sweep vertically, and now my intermediate tensors only have t dangling legs. If t is very small, this can be a big savings. So I sweep down like this. My runtime is, I have n steps, and then my intermediate steps take me time exponential in t. So if t is constant, this is a really dramatic savings. And this is why one-dimensional low-depth circuits are easy. So what about 2 dimensions? So you now have L by W qubits evolving for time t. So you get a little block here. And similarly, we can kind of sweep. If we have an L by W rectangle that we sweep across this way, that's going to be time 2 to the LW. That's 2 to the n. That's the naive simulation. But of course, we can sweep in the other directions also. You kind of get the idea. But once I made these PowerPoint animations, I wanted to show them. So you can sweep in any direction. And the runtime is, it's either 2 to the LW or 2 to the LT, 2 to the WT. Pick whichever rectangle you like. You're probably all very familiar with picking minimal surfaces, right? So this is what's going on here. So let's say specifically if I have a constant depth circuit on a root n by root n grid, you'd say, OK, I know the answer. That's going to be time 2 to the root n, right? And it's kind of like root n qubits on a line evolved for time root n. And now, so far this is all what we knew previously. Our contribution is to say that yes, you do have a 1D effective evolution. Simulating this 2D system does look like root n qubits evolving for time root n. But this is no longer a physical evolution. We took these tensors and we glued them together. Those don't look unitary when you kind of turn them on their side. I'll show you more pictures of turning them on their side. So this looks like a non-unitary evolution. And you can think of this as what it's like is you do a unitary and then you also do some measurements. And the unitaries will create more entanglement, which will make it harder to simulate. But the measurements will reduce your entanglement, which will make it easier to simulate. And there'll be a competition between 2 effects, which leads to interesting physics, maybe a phase transition, and can lead to the simulation being easier than than you might naively expect just by looking at the dimensions. And what we find is that if you do depth 3, then you're in the area law phase. So low entanglement, I'll explain more what that means, which gives you a polynomial time classical simulation for random, approximate simulation of random circuits. So this is something that we know. If you want to do it exactly, or in the worst case, is hard. But in the kind of the operationally relevant case where you're allowed a small amount of error and where you choose the gates randomly, then this becomes easy. OK, so how does this cheaper tensor contraction work? You have this root n by root n grid. The effective time evolution is you have root n qubits evolving for root n time. But the evolution looks like you've taken the 2-qubit unitary and turned it on its side, right? So these would be the top legs would normally be the inputs, and the bottom legs would be the outputs. It's unitary. If you make it a matrix that way, like you assign this to be the columns and these to be the rows, that would be unitary. When you turn it on its side, it's a little bit like here what she said about the partial transpose, right? If you take a density matrix and partially transpose it, it's not always positive anymore. If you take a unitary and you mix up the input and output legs, it's not always unitary. And so you can think of that as corresponding to a unitary followed by some weak measurements, ones that maybe reveal some of the information about the state. And so this gives rise to an approximate simulation where if you have your 1D state and the entanglement across the cut E is limited, then you can write this as a matrix product state. And in general, the bond dimension will scale exponentially with the entanglement across this cut. And so our algorithm is you do tensor contraction, and then as you write this thing as a tensor, you write this tensor as a product of little tensors. So each one of these little vertices has 3 legs coming off of it. One physical leg of dimension 2, and then these vertical legs of dimension that can be a parameter. This is called a matrix product state. And the dimension of these legs, you have to choose to be large enough to accommodate the entanglement that's there. But you don't have to let this get arbitrarily large. So you can truncate it. If the entanglement is E, you can truncate it to be exponential in E, and you'll get a pretty good fidelity representation of the state. And so the runtime is n times something exponential in the amount of entanglement. So that is our algorithm. And then you'd like to know, well, does it work? And my evidence for it working is inconclusive. So there's sort of two answers to does it work. One is we ran it on a computer. We ran it on a 400 by 400 grid. By contrast, Google's 53 qubits would have taken a gazillion years on a normal computer. But if you do it in constant depth, even a 400 by 400 grid, our laptop did not run for 2 to the 400 steps, right? It took way, way, way less time than that. It ran very well. We seem to be mostly limited by machine precision. However, that is not a proof. I'm a theorist. I want proofs. We do not have a full proof. We have proofs of related facts, which I'll describe to you now. So what we would like is a proof that if you do this 1D effective evolution, you're in the area law phase. There's very little entanglement. And we would like this for Rayleigh entropies that are between 0 and 1. And what we proved instead is for Rayleigh entropies, as you can probably guess, for integer values of Rayleigh entropies, especially for k equals 2. So what does that say about k equals 0.9? Is a matter of opinion. So let me now tell you about this last part where we relate, where we calculate some Rayleigh entropies and prove phase transitions in quantities that are related to what we want, but not exactly the same. So what we want to do is we want to show that these effective dynamics, just to recall, give you not very much entanglement. So how do you measure entanglement? Well, if you have a state rho, let's say it's pure, and you look at a subsystem A, you might look at expectation of trace rho sub A to the k. If that state is pure, this expectation will be 1. If the state is mixed, this will be very small. So if this number is big, the state is not very entangled. If it's small, the state is more entangled. There's significant asterisks concerning the value of k, but that's the basic idea. It will be convenient for me to generalize and not have qubits at every site, but q-dimensional particles. So now we have two parameters, q and k. And now, to evaluate this expectation trace rho sub A to the k, the amount of entanglement, we relate that to the partition function, or more precisely, the ratio of two partition functions. One of them with a twisted boundary condition, one of them with normal boundary conditions. So if k is equal to 2, you get something that actually looks very nice, like an anisotropic Ising model. And the boundary conditions correspond to the region that you want to calculate the entanglement of, or the entropy of. So if the region is A, you put one boundary condition on region A, and a different boundary condition on A complement. And then you basically want to figure out the cost of the domain wall. And so you can imagine there are two different regimes. If this is in the ordered regime, then the domain walls kind of look like this. And the cost goes like root n. If you're in the disordered regime, then the domain wall doesn't cost very much, and the cost might be constant, just basically dominated by this little boundary right here. So that is the idea. The precise model, the precise thing that we get, looks like this. We take every unitary and we turn it into this little gadget that goes into our StatMech model, a lot like what you saw in Xi's talk. And the gadget involves vertices that are labeled by permutations and edges that are labeled either by Weingarten functions or by these Graham matrices. So what are those? So the G vertices have a weight that goes like Q to the minus distance between these permutations sigma and tau. So it's 1 if the permutations are equal. Otherwise, it's going to be some power of 1 over Q, depending on how far apart they are in terms of transpositions. So that's the matrix G. Notice that all the entries are non-negative. And then the inverse matrix is the Weingarten matrix. That's going to have some negative numbers. So a priori, yes, you do have a partition function, but it's a partition function where some of the legs have negative weights. So that is not so great in terms of me talking about ordered and disordered phases, but that's what we have. In some cases, like k equals 2, we can decimate. So if you decimate all the sigma vertices for k equals 2, you get a nice thing where everything has non-negative weights. So that really can be interpreted as a partition function. All this ordered, disordered transition stuff makes sense. We conjecture, and this is supported by numerics, but we cannot prove it yet, that for general k and q, there's some decimation that always gives you non-negative weights. But we do not have a proof of this fact. So what does the phase diagram look like? There should be an ordered and a disordered phase. When q is very small, like 1 plus epsilon, this looks like a high temperature Potts model, which we understand pretty well. Of course, q is supposed to be the local dimension, which should be like 2, 3, 4, etc. So 1 plus epsilon does not have a very strong physical meaning, but at least in terms of the phase diagram, we understand it. When q is very large, these are the random tensor networks that you're familiar with from Xi's talk, from a lot of the it from qubit work on random tensor network involves q large. And for k equals 2, we can appeal to results from the literature to show that there's a phase transition above q equals 3, which means that in the quantum computing relevant model where these things are qubits, we are in the disordered phase. And disordered phase means not very much entanglement, which means our simulation algorithm works. Hooray. However, this is still for k equals 2, right? Ultimately, we want k to be between 0 and 1. So I would call this a proof of something closely related to what we want, but not exactly proving that the algorithm that we ran works. We do not yet have a proof of that. I should say I'm sort of disparaging our proof. The algorithm we ran is self-certifying, right? So it also, you're truncating these matrices, throwing away the small singular values, and you know how much you throw away. So just the fact that we ran our algorithm is sort of a proof that it works on those instances. We just don't have a proof that it works on average. So how does this relate to random tensor networks, which you might be more familiar with? So again, q is a local dimension. We want expectation of trace row to the k. We get these gadgets. If you take the expectation over unitaries of u tensor k and u star tensor k, you get a sum over permutations labeled by the Weingarten matrices. And if you instead take it over matrices G that are drawn from the GUE ensemble, basically random matrices full of random Gaussians. Actually, I'm sorry, maybe I shouldn't have said GUE. I think that might just be random Gaussians. I made a mistake there. Just G is just full, every entry is an IID Gaussian. Then basically Wick's theorem tells you you get a sum over permutations. And you see the only difference is here we have Weingarten and here we have the identity. And Weingarten is very close to identity in the regime where the local dimension is very large. So in that regime, when the local dimension is very large, k squared is much less than q, unitaries, their low order moments look a lot like Gaussians. And Gaussians don't care if you relabel the legs, right? It's just every entry is an IID Gaussian. So if I turn a matrix on its side, who cares? It looks almost the same. So in the regime that you may be more familiar with of random tensor networks with very large q, there's none of this issue of turning things sideways of which direction is unitary and which direction is non-unitary. Everything's Gaussian. It all looks the same from all directions. Gaussians look like unitaries. It all kind of gets simple. The regime we care about is of small q, where this stuff breaks down, where it looks unitary in one direction and non-unitary from another direction, and that makes all the difference to whether our simulation works or not. Let me close with a few open questions. We have this phase transition with k equals 2. We'd like it for general k. We want to prove that our algorithm works. I think it'd also be interesting to understand random tensor networks with low bond dimension better. To what extent do the results that are known about them break down in that case? For random circuits, we don't really, we talk about phase transitions, but we don't have the sort of universality classes that we would like. We just have results about very specific models. We don't have good ways of relating one model to another one. So if I say, for example, measure each qubit weakly, or measure 2% of all the qubits with a strong measurement, I don't know how to relate those models, but intuitively they seem pretty similar. We'd like to relate these to time-independent Hamiltonians, and in general to figure out the boundary between computationally easy and hard to simulate. And I guess one more question I should have put up that was inspired, I thought of this in earlier talks. You know, we're often computing various Renyi entropies. And there's not always, I never know kind of which one we're supposed to be computing. In this talk, we do actually have a clear, concrete motivation for Renyi entropies at less than 1. And so it'd be interesting to know kind of how those relate to the other Renyi entropies for these types of states. And I'll conclude by saying, thanking my co-authors. So Saeed is the author of the 2D and up paper, Fernando and Michał of the 1D papers. The general geometries with these co-authors. 2D simulation is with a different group. Here they all are pictured. So thanks to them, and thanks to you for your attention.